And I'd also like you to, I cut the testing time out.
Okay, so we're going to get going here. I give you a little bit of extra time in anticipation of the presentations that you're going to be giving me soon on ID1. I'm looking forward to them. This afternoon, if someone could get the lights for the left, I think it's the left button there, if you push it. A button is good. Yeah, thanks. So last time we had started a look at some elements of test design. I had noted that there's broadly different levels of tests associated with a system. At the low level, unit tests written by the developers, although sometimes not the developer who wrote the code, but another developer in a process called buddy testing, which will test low-level design. High and medium-level design, articulation of several different components, say several classes of a system, might be tested with integration tests. They're not only testing one item in isolation, like one class, using mocking to mock out other classes, but instead they are deliberately testing that item in the context of its working with other items. Architecture use cases, common use cases, will commonly be attacked with system tests and with acceptance tests, particularly in certain sub-industries, being used to validate customer requirements. And last time we had talked a little bit about the use of regression testing, different test perspectives, glass box and black box. Could anyone remind me, if we consider black box versus glass box testing, what's the difference between them? What's the salient difference between a black box test versus talked about as a glass box or white box testing?
The black box, you don't know how it's implemented. All you know is that you give it something, you get what you want back.
That's right. So all you know is what it does, not exactly how it's done. And black box testing and glass box testing can all be applied at various levels of a system. We could apply them at the level of a function, a given method. What might give us the information we need to do black box testing about what it does and not the how it does it? What's good programming practice to provide along with a function? How about those who are in 470? Preconditions, postconditions. Yes, exactly. The mechanisms that we use to provide clients of that method or function information on what it guarantees. These are absolutely essential things for solid software engineering, really solid software engineering, because without them, the client, the one who's using that method or function, doesn't know with confidence what it guarantees. They might guess from its name or what have you, or otherwise have to seek recourse to more extensive documentation, which does provide those specifications. For the person who creates that code, the function or the method, and is considering providing preconditions and postconditions, it's essential, because those preconditions and postconditions, what benefit do they offer to the creator of that code? So if I'm going to create a function, check dependencies, or are dependencies valid, something like that. What benefit is it to me to provide preconditions and postconditions? How does that help me as a creator of this code? Anyone? So it takes some time, obviously, but how does it give me benefit? I would argue there's many benefits coming from it. Give me a couple.
Keep you focused.
Sorry?
So keep you focused.
Keep me focused. When I'm writing this, I have a sense of what's what is to be legitimately assumed, and what I'm trying to accomplish by that. a crisp understanding of what this function is doing. So that's good. So while I'm writing the code, where else do these help besides just writing the code?
When you come back to that later time, so you can quickly understand what
Quickly understand what's being done, what's the intention behind this code. Good. How about something else? How about that lowest level there down here? If I'm writing unit tests, do you think those might help? Writing unit tests against this code? Someone else's? They help me hugely. They help me check what things should I test ahead of time are the case, perhaps with assertions, and what things for the post conditions should be the case after I call this with valid preconditions, what things should be guaranteed. That's good. And if someone else is coming to this, a tester, for example, even at the level of methods or functions, these are good things that can drive tests, drive black box tests. You specify the what and not the how. But what else, what other benefit does this give? To me, as the creator of this method, what other benefit does it give me in terms of future evolution? Well, ladies and gentlemen, if I go and later evolve this code, I know what things other people are counting on. I know what things they're counting on, what things, by implications, they shouldn't be counting on. This is really important. The Windows API I hold up as an anti-pattern in this regard. People came to rely on certain bugs within the Windows API. They weren't promised by the API, but they came to rely on them because it wasn't clear if they could rely on them, and so they did. And so when Microsoft came to revise that API through successive versions, it had to maintain backwards compatibility to the point of bugs. You don't want that. You don't want people to be counting on all sorts of internal, detailed vagaries of exactly how this does it. You want to be able to state clearly what you promise and under what conditions you promise it, so that you have the freedom as the developer to evolve it, the implementation in ways that you see fit. To use more efficient data structures, more efficient algorithms in it. People shouldn't be counting on every single little detail of this code. Just what's promised. Does that make sense? Okay. So when it comes to performing black box tests, and when it comes to performing glass box tests, in both cases, we're using different information. Black box tests will often use specifications or requirements or guidance, help documents for the user, things the user would understand are promised to them about how the system should behave, help manuals, what have you. By contrast, glass box tests are using the internal details of the implementation. So, in short, the black box tests basically are testing the consistency of the implementation with the requirements, whereas structural tests or white box tests are testing how well does the implementation match the design, match what was intended for the implementation. To what degree is the implementation actually carrying out the plans of the design? That's particularly true. I mean, some structural tests can also test does the implementation indeed match the promises, the behavior that was guaranteed, the what it's supposed to do. But often they're testing sort of the internal mechanisms, and does that in fact accomplish what was planned. Okay, so here we have black box tests, structural tests, and we're going to see that these can be applied at many different levels. And it can be applied at the very low level, like call graph coverage and logic within a method, but it can be examined at the system-wide level with control flow among broad areas of the system. I started to talk last time about creating test cases. And these are very actionable items for your projects. I would love to see, starting in ID2, some serious thinking going on as to how we're going to test certain user interface items, how we're going to test certain algorithms, how we're going to test certain certain key methods of the system. And we start to talk about equivalence-based testing. Can anyone remember for me the essentials of of this message? So equivalence-based testing. Why do we talk about equivalence classes? What is an equivalence class? How might we define one here? If we consider a user form. Okay, so here's a form, and it's for the SCOGA tool for Dr. Basra. Here's your form. Maybe there's multiple tabs, and the tabs might not be disjoint in terms of the questions asked. So on a given tab, maybe there's certain questions asked, and that has some overlap with some of the items in other tabs too. So it's not disjoint contents. But suppose there was, a 3 text boxes and a up-down indicator for some number that was entered here. So this is a numeric. These are text boxes. Maybe it's first and last name and middle name and age, something like that. Okay, so when we think about equivalence classes, what should we be thinking about? How do we use that to inform our testing? Can anyone remember from last time? How do we use equivalence classes to test better? Remember, we can't test everything. There's just no way we can do exhaustive testing. So we have to choose our tests carefully, judiciously, so that they cover a reasonable range of things. They exercise the system's functionality. Give me a sense of what some equivalence classes might be. First of all, should we think about equivalence classes that are illegal as well as legal? Give me some illegal equivalence classes you might try here. So let me put it this way. So I could generate random items to put into these, just generating random characters of lengths drawn from some distribution and putting in random numbers. Is that going to be a very efficient way to test this thing? Imagine if I gave you folks an hour to test this. I said, break it. Break it. Try and find where it's broken. Do you think just testing with random entries is going to get you very far? No, it'll get you for the first couple. It might, test something. It's not totally out to lunch, but eventually you want to be clever about testing these things. So think about names. What might you test there? Okay, first name and last name. What might you test?
An empty name.
Empty names, good one. How about another thing?
Numbers.
Sorry?
Numbers.
Okay, numbers for names. Yeah, I like that. Okay. Others?
Obscenely long name.
Okay, yeah, that could be interpreted several ways, but it would be a long name. Okay, so it's a very, very long name that it doesn't break the thing and say overflow. Okay, that's great. I think the Thai name for Bangkok is something like 200 characters long or something like that. So you could put that in there. Okay. So what other things could you try?
You could put SQL into there.
Put some SQL in. Okay. Yeah. That would be interesting. See if you could elicit some extra information from the system with that. That's good. Does it reject SQL characters? And in general, does it reject characters that are not plausibly part of a name? And this is where you'd have to look to the documentation. What is a legitimate name for this system? What are the requirements? Does it allow 3 asterisks or three apostrophes in a row, or an asterisk alone? There's going to be some rules for legal names, and you want to try some illegal and some legal names. Probably you want to make sure it will handle, in terms of legal names, give me some ideas of things to test there for a last name. Give me some things to test for a first name or for a last name that would be reasonably common last names you want to be sure to test.
Hyphenated.
Hyphenated. Okay, good. Yeah. Another one?
With spaces.
With spaces, De Angelis, right? How about another one?
With
Yeah, okay, okay, there might be periods, yes, that I may have seen one name in my life which might have a period in it. That it's possible, yeah. How about others?
Names with accents.
Okay, accents in them, yes, exactly. So multilingual names go beyond the ASCII characters, right? Excellent. How about other names that might cause problems? Well, there's actually quite a few once you start thinking about it. Again, it would define how the system's defined. There are names I know that start with an exclamation point, for example. Like Bushman, Kong Bushman. To start with an exclamation point. So there's going to be a certain delineated set of names that are viewed as legal. And the point is, you don't want to just thrash. You don't want to flail against the system, just trying random things. You want to be at least testing it in a somewhat systematic way. You have an hour. What are you going to do during that hour to have the best chance of finding things? Put in some legal, put in some illegal, test the boundaries of what's legal. Remember, your goal here is often to try to provide feedback on things that break it or things that aren't working properly. You might try names that have that are very, very brief, as well as names that are longer, that have multiple parts in them, and go at it. And similarly for this number, you might try negative numbers. You might try 0. You might try positive integers and make sure that it's working properly. You might try going down from 0. So the point is, you're not going to flail. You shouldn't flail. Flailing is just not going to get you very far. What's going to get you further is judicious choice of a couple types of names, trying them out, and not spending a huge amount of time trying, names that are just single words. Maybe try a couple of them, but then you'll try some multi-part names with dashes, with spaces, with apostrophes, etc., and try some names with some unusual characters. Maybe cases where the first name is blank. I've met several people in my life who have no first name. They have just one name for them. And some where the middle name is blank. You want to try some of those edge cases, the cases that are just on the edge, what's allowed, for example, 0 here, and some that are definitely illegal, some that are legal. And the goal is to have a fair coverage of different cases. Okay. So we talked about it in the context of seats last time. So you want to try, aisle, middle, and side seat, maybe exit rows, and so window seats, and then a business and non-business cabin. Okay, talk for the square root function, picking appropriate sorts. The goal here is to take your limited time and try to have the best chance of exposing a bug. How do you pick these equivalence classes? Well, do they sort of put the system through similar paces? There's going to be whole equivalence classes that are kind of handled similarly. They're similar to each other, and there's not a lot of use about pouring a huge amount of effort to many of those cases. You want to try a few and then move on to others, and particularly test the kind of borderline cases. Okay, so we talked about this last time, and then I started to get into a discussion of systematic testing, where we might, instead of having a case like that, we might instead have drop-downs, next to each, which only have a set of possibilities. And if you have drop-downs, which let you choose, say, one option for these each, to pass the red face test, to sort of have any confidence that your system is really operating well with respect to these inputs, you want to test at least once for each possible value of this, at least once for each possible value, once for each possible value of that. Otherwise, how can you be sure that a given value isn't handled? If these trigger different sorts of results. If they're just, different cities within Saskatchewan, maybe you test a big city and a small town or what have you, and something in between. But if these are pulling down rather different cases, you're going to want to test them, each of them, one time. So this is what I call weak systematic testing. You are testing each one at least once of these notable cases. Now, something that I referred to in the closing minutes last time was what are called orthogonal arrays. And the idea here, ladies and gentlemen, goes beyond this weak systematic testing where we are testing each of these one time. And instead, what we are trying to do is test all pairs of values. And what this type of testing helps us do is dramatically reduce the number of cases from all possible combinations, but still to find compatibility problems. Problems where, if you pick A for this and item A for this drop down and item 1 for the second drop down, they're going to conflict with each other. So they basically guarantee not just testing each option for each of these one time, which is a bare minimum, but testing pairs of possible values. Okay. Now, this may seem only appropriate in some cases, but it's particularly valuable if you're dealing with like configurations of machines. This is an older slide now, show it nonetheless, but the idea is here that we want to test our system with different media players on different browsers, different web servers, and different operating systems. Okay, and we want to make sure that it works with all of these. And one option would be to test it with each browser, and test it with each plugin, and test it with each server, and with each operating system, each in isolation. What wouldn't that get? So suppose we were to do that. Suppose we were to consider browsers and test it with each browser. Plugins, test it with each plugin. Servers with each server, each operating system. What wouldn't that capture? What cases might that let through? Can anyone tell me?
If the browser works differently somehow on a different operating system?
Yeah, so maybe the problem isn't Netscape itself for Mozilla, its progeny, but maybe the issue is really Mozilla on with a backend or with Media Player, which was an earlier media plugin, or with Real Player. Maybe by itself the browser works. Maybe the Real Player works fine in one browser, but it doesn't work fine in Mozilla. Quite common case. It's not that each is broken, it's there's a compatibility issue between them. A similar issue might be, maybe the issue is not Android 6 in viewing your web app. Maybe it's Android 6 with the Chrome browser, or Android 6 with the built-in Dolphin browser, or what have you. So there are cases where the problem is not in any one item. The problem is compatibility issues between two items. That it's when you have A for the first choice and B for the second choice that's when things go wrong. So an orthogonal array helps you check all pairs, that you've gotten all pairs of them. And it does so without enumerating all possible combinations. Let's consider the combinatorics of this. Suppose that we had here, so suppose that we had, for each of these items here, let's just consider these three here. Suppose each of those had 4 possible items, okay? So there are 4 possible ones for this first dropped out, 4 for the second, and 4 for the third. If we were to test all possible values of combinations of these, how many combinations would there be? Thinking back to 260. How many combinations? If any of these could be chosen with any of these, with any of those, how many combinations? Okay, let's consider it this way. Okay, so we have 4 possible values for this guy. For each of those 4 values, how many values do we have for this one? 4, right? And for each of those values, each of those 16, 4 of these times 4 of those, all possible pairs, we have how many of these? 64. All right? 64. All right? Yeah. Happens to be 2 to the 6 because each of these is 2 to the 2. 64. Okay, so 64 possible combinations of all possible ones. Now, if we do this in a pairwise fashion, we can enormously reduce that number. And I think it'll be reduced to somewhere on the order of 10-ish. I'd have to do the computation, but we can reduce it dramatically. So instead of having, in this case, 4 possible categories, each of which has 3 possible values, with the results being, what, 81 times 3, 243. That would be 3 to the 4th, I think. You have 8 test cases reduced down. And the idea is that these test cases within this orthogonal array have every possible pair. That's not to say every possible combination, but every possible pair. So there's at least one case where Netscape has no plugin, one case where Netscape has real player, one case where it has media player. There's at least one case where Netscape is paired with Linux, backend with WinNT, and with 2000. Same thing with IE. So the point here is that we have pairwise checks. So there's going to be at least one of these test cases where any given pair exists among these 8. Now, a given one of these, a given row, is going to test several pairs. For example, IIS on Win 2000 or Netscape 2 with no plugin. That's going to be tested by this first row. So it's going to be testing and none with IIS. It's going to be testing several pairs at the same time. But any given pair is destined to be examined within the small number 8 rather than 243, which is not a bad economy. It's not a bad economy in terms of testing. So you don't have the luxury of testing all possible values, all possible combinations. So what you do is you test pairwise combinations to see if there's compatibility issues. If 2 choices, when you have them together, they break the system. And that's quite common, that you have these pairwise issues. Does it test all possible triplets? No. But triplet incompatibilities are less common than pairwise incompatibilities. Often we get stuck because you can't use this on that. It's a pairwise issue. We can't do this one with that one. It's not that this is broken totally, it's just we can't use it in this context. This certain backend doesn't work with this version of struts or what have you. Okay. So orthogonal arrays test all possible combinations, and they can be very efficient in doing it in a small number of cases. And you will find quite a few tools listed out there which can actually generate these things for you. So you fill in the possibilities, you fill in the different choices here, and it will spit out an orthogonal array that will figure out how to test these things or how to explore them in a way that all pairs are generated. Any questions about this idea of an orthogonal array? People okay with that? Tools out there that will spit these out for you. There are ways of doing it manually, but in this day and age, it's not worth your time. You can find dozens of tools listed that will help you with formulating these sort of test cases. Okay. Right. So yeah, it can reduce by remarkable numbers. For example, 36 to 9. This number to 144 to 199. You can run these number of test cases often even through a UI. They're small enough for a professional development team. These type, you don't have a chance at all. You're not going to be able to run that number of test cases. Okay, I want to talk about one other type of testing before we go into path testing. And path testing is a method I will request of you. So it's good that you're here. It's good that you're here today. Let's talk about confirmational random testing. This does come up in a fair number of cases. you have a problem that is hard to figure out, but fairly easy to check. Either to check its full correctness, or, mark my words, to check that certain features are true. Sort of classic example of this would be something like the square root or isomorphism problem. So it's hard to figure out, perhaps, if I have a number, what the square root is. You have to go through a lot of operations. But given that, it's very easy to check if that's the square root. Square root algorithm is, decently involved. If you give me the square root of a number, I can just square it and see, does it give the original number? Right? So it is with graph isomorphism. If I give you one graph and I give you another, and I say, is there an isomorphism between them? Is there some mapping of vertices of one to vertices in the other, which in some sense means that the same graph, it's just ordered differently in terms of the specification. That's actually a hard problem to figure out, extraordinarily hard to figure out efficiently. I believe it's NP hard for those for whom that's a significant state. I mean, if you could solve that, you can solve you can solve a huge number of problems efficiently. But if you give me an isomorphism, I can check it really easily. Is there a mapping between them that's consistent? Ladies and gentlemen, in your projects, there may be cases where you have algorithms that attempt to derive something, and it's a complicated algorithm, but at least there's properties of it, of the results, that you can check. Is this a plausible result? So let's think about a case where you're reserving a flight. So last night we're on orbits looking for flights, as well as some other airline search engines. Okay, so looking for a flight from here to Ottawa. If I were looking for that, what might, and I want to find the cheapest flight, let's suppose, or the shortest flight. What might I do to check the results that would give me, some chance of finding a broken algorithm? If my algorithm wasn't correct to find the shortest flight, what could I do? First of all, give me some features I might check about the results. So it returns back a flight that says, go from here to here, here to here, here to here, in Ottawa, what have you. What could I do to check if that's a reasonable result? So suppose it's multi-leg. So maybe it's from here to Melbourne, Australia. What could I do to check it?
There's no backtracking?
Okay, yeah, there shouldn't be any backtracking. I shouldn't fly from here to Vancouver to Sydney, and then back to Vancouver, and then to Sydney again, before finally going up to Melbourne. Okay, so I like that. There should be no repetitions. I shouldn't be visiting Saskatoon in a giant loop, right? Like the man who never returned in the Boston subway. Go look it up. Okay, so that'd be one thing to check. How about another thing to check? I mean, the goal here is not to have perfection. The goal is to find bugs. The goal is to find issues. So give me an obvious thing to check. Is it a continuous path? You go A to B, B to C, C to D. Great, from my call. Is it a what?
The flight time?
The flight time. Okay, yeah, the flight time should be greater than 0, right?
Sorry, I mean like the time between two flights.
Oh, the time between two flights, it should never be negative, for example. The next flight doesn't leave before I arrive, right? Yeah, that would be disadvantageous. Okay, so that would be a good thing to check. How about another thing? How about very basic thing?
If you actually get to your destination.
So you get to your destination. You start where you start and finish where you finish, right? I mean, look, if it doesn't satisfy that, it's hosed, right? I mean, it's totally broken. But if you're not testing it, who's going to test it for you? Who's going to test that for you? Maybe 1 out of every 10 times it has a bug and it returns this. And if you're not testing it, there ain't nobody's going to be testing it for you. Get it done, right? It's something obvious, but it's low-hanging fruit. Okay, give me another thing that can be tested.
Are there tickets available for each flight?
Okay, good. Yeah, are the tickets available? In terms of sort of this being the cheapest flight from here to Melbourne, what could I do? Oops, sorry. I could look at a randomly chosen one, right, from there to there and compare the price. At least it should never be above that price, right? Again, it's not perfection, but could it find bugs? Yeah, it could find some big bugs, and that's what you want. The goal here is not to have the perfect test. The goal is to have a test that might quickly alert you to problems. And these are all great little examples of things that would alert you to problems. So confirmatory random testing, throw in a random start, a random finish, get back a result, and see if it matches these properties, right? Contiguous is great. A to B, B to C, C to D. Pretty good. I remember one flight I was on. Gosh, where was it? I think it was through Shanghai. I flew in one airport and I had to leave from another airport in the same city. And we did that for London too one time, Gatwick and Heathrow. But by and large, it's a good one. You can put in some exceptions. So the point here is that testing is not perfection. Testing is about finding the quality issues quickly. And there's often, even if you can't have this nice, pristine example here, you can often test broad features to see if it's sane, if it just looks, on the face of it reasonable, right? And use that to discover problems. You could use it to rule out whole classes of sort of totally broken cases. Pretty easy to do. Pretty easy to do. So if you have a search function in your app, or you have a website where the user should be able to enter some information, get some information back, you should be able to do some confirmatory testing. But that's just through the UI. Think about the guts of your algorithms. Think about the guts of your system, ladies and gentlemen. It's not just about through the UI and the tickets that I search for through the UI. That's all great, and that will be most obvious to the user experience. But it's also what's going on beneath the covers of your system in terms of searching for information, etc. You should be able to test that a given function returns a value that's not out to lunch pretty easily. So figure out for your cases what out to lunch means and put it into effect. Does that make sense? Test the broad essentials. Don't get caught up in perfection. It's a matter of, can you sort of quickly test some whether it's sane, and thereby bring bugs to light that would otherwise be missed at any level of a system. Okay? Are we okay with that? Okay. At least I saw one head nod. Hopefully not from sleep. Okay. So now I want to go on and talk about this. So I would like that. I would like you to have at least some confirmatory testing. And now I want to talk about another thing I'm looking for you. I'm looking at you, kids. And it's about coverage testing, okay? I want you to make use of what we're about to talk about. And it's pretty straightforward to do at its most basic level. It's like providing me with a test matrix. That was one of the things I asked for before. Provide me with, some continuous integration capabilities. Great. I want you to do this as well. Coverage tests. Okay. We're going to talk about a bunch of different types of coverage this week. State-based coverage, where we're covering nodes in a system. Now that's going to sound very abstract. We'll come down to some specific. Transition coverage, where we're capturing not just reaching each node, say state, but the transitions between those states. Prime paths, which are a particular way of kind of exploring the system. And as time allows, probably not this week, we'll cover constraint-based coverage as well. Now, the key thing here, ladies and gentlemen, like so much of what I'm talking about, coverage testing occurs at many different levels. Okay? It's not just at the black box level. It's not just when you use the system. But at the least, that's what I'd like you to provide for me. You should be able to think about how do you conceptualize your system as a graph? Nodes and edges between them, vertices and edges, whatever terminology you want to use for it. And think about the user's actions as bringing them from one vertex to another. So I click this next button, it brings me here. I see this page. I enter this information, and it sends me back to that old page. I go back to that vertex, okay? You should be able to conceptualize your system at a high level in this way and then apply these tools of coverage. But the same techniques can be applied at the level of your internal algorithms, at the level of your flow within your system. Okay, so here's an example of a state diagram, also called an activity diagram. I don't know how much you folks in 270 hit on UML diagrams.
A bit.
A little bit? What types? Like state diagrams? Did you talk about a class diagrams? Swim lane diagrams? No. Sequence diagrams? No. Okay.
370.
370, you talked about this one? Okay. Okay, so here's a automated teller machine. Gives out bank notes, right? Here are some states that it might be in. Okay, so you insert your card, and what does this indicate? This is a time-honored way of indicating what?
Decision.
It's a decision point. Yeah, it's conditional. Either the card is not recognized or the card is recognized. The card is not recognized, it ejects it. If it's recognized, it prompts you for the PIN. Puts up a screen asking you for the PIN, and then you enter the PIN. And if the card is expired, it may confiscate the card. Any of you had this happen before? That was a lot of fun. I was about your age, and I know you think like these things didn't exist, right? We were like hitting on making stone tools or something. I'll tell you this: I have worked on stone tools before, but it wasn't because of lack of technology. Yes, I had the card confiscated from me. It was most rude. I entered it, and it just sucked it in. That's it. Sorry. I'd go to the bank, buddy, something along those lines, and it took it, and I never got it back. So if the card is expired, it confiscates it. If the card's not expired, if it's lost, it confiscates it. That's kind of a neat thing, right? If it's been marked as lost, otherwise it checks the PIN, and if it's invalid, it can also confiscate it, or it can, if it's less than 3 tries, it'll prompt again. This is a high-level diagram of an ATM process, and you can see it. I mean, it makes sense in terms of the states the system could be in, right? The sets of possibilities, the sets of user interactions that lead to these things, including the mainline process where, that we like to think of as software engineers, where we, prompt for the PIN, we enter it, it checks the PIN, it prompts for the transaction, we select the account number, and then we dispense the cash, print receipt, eject card, boom. That's the mainline thing. And we love to think about that common case, but the fact is a lot of these other cases are as important in terms of the whole economy of handling these cards. So this is a high-level diagram of the flow of a system amongst a bunch of different states. These are states or nodes, vertices, and then we have transitions between these vertices, which are often conditional, but not always so. Right? Now, having formulated your system like this, we're going to use this sort of diagram to derive test cases. Could you give me a sense? What sort of test cases might we derive from a diagram like this? Why might it be useful to have a diagram like this to formulate a test case?
You can make sure you test each path.
Exactly. Make sure you test at least with some coverage. Now I heard an interesting comment there. Your name?
Evan?
Evan. So Evan was saying test each path, and I like where he's going with this. At the least, we could think of a couple of things to test here. Give me one obvious thing to test. All the conditions, right? All of these conditions. At least once you go here, at least once you go there, right? At least once you test it with an expired card. At least once you test it with a card that's lost. After all, how could you stand in front of someone who's sponsored this project and say, our system is ready for deployment. If you've never tested this case, right? If you've never seen it suck a card in and confiscate it, how are you going to know it's going to do that, especially with that sound, right? And you know, you want to at least test it to have some confidence it's working properly. Similarly, to make sure that it confiscates after 3 tries, not 10 tries, right? So if we're not testing the conditions, we might be missing a lot. At an even more basic level, though, we might be testing that it hits each state, right? I mean, look, if you've never been in a state where it ejects the card, this state here, or where you have to, where you have to print the receipt or what have you, how can you be confident that that area of it is working? If you've never confiscated the card for any reason, how are you going to be sure the speaker is working properly, right? So the point is, we could test states, we could test transitions, we could test paths, in fact, which are paths from the start to the finish that might go through different use cases. But once we've defined this as a diagram, as a graph, edges and nodes, we could start to think about how to leverage testing to explore it well, or at least not to explore it embarrassingly poorly, right? If we've never gotten here or here, it ain't done, the testing. If we have, then we can have some confidence that it may still have bugs in it, but at least we've ruled out broad classes of dysfunction, right? Does that make sense to you? So much of what we're going to be doing today and Thursday is talking about these sort of diagrams. And much of what I want from you soon, though not for 4 o'clock, is a diagram of your system as it evolves in this sort of way. So let's talk about that. You folks are not designing ATMs, for better or for worse. Instead, you are designing web apps, or you're designing systems that are based on smartphone apps. So tell me, what for your systems, what might the states be?
Login.
Okay, a login screen. I like it. Login screen. Yeah. How about another state? Let's talk about the Vidarian supremacy. So for this project, what are some of the states? So there might be some sort of login mechanism. What else might be the states that it could be in?
A blank slate with no project on it.
Okay.
Various states of, say you click a button to drag one on or something like that.
Okay, so there might be buttons where you've selected different items.
Yeah.
Buttons where it's actually being dragged in, like that Vidarian visage, right? Being dragged around. That's in a state of being moved, and that's different from once it's dropped, right? Once it's dropped, there's some concerns about it that don't apply as much. Okay, so there's a couple states. How if I go to print it? Might there be a state associated with printing or exporting it, where it's looking for some information about, how to export it or how to share it, or how to perhaps in terms of printing it out or rendering it in another format, storing it as a JSON file or something. There could be states associated with the UI there. Okay, so those could be some states, and I would argue that you'd have to think a little bit. Is it a different state if I'm dragging in a torso image, or I'm dragging in a connection? Is that a different state? And I would argue that it might be, right? Because with a connection, it can if you're dragging. Think about it. If you're dragging a thing which includes a connection, that connection may have to drag with it, right?
Yeah.
And so there might be different states associated with that where it's updating related things. Okay, how about the case of the SCOGA? So this case of this user interface for entering patient information of different sorts or what have you. Again, where there might be real overlap between different sort of views of this. What might some of the states be there? Anyone?
Selecting a patient.
Selecting a patient, good, okay, yeah. So maybe initially there's no patient and you select a patient. And how about additional states for that patient? Where there might be different subsets of information that
Yeah,
you,
or separate forms you'd have to choose.
or separate forms that you'd have to choose. So there might be a way of viewing one form, viewing another form. I like that. Okay, how about for the bed manager, folks? Give me a sense for the bed manager. What are some states?
You have the login states.
Okay. I like the login state. What else? You. Think about what Alan McLean wants. What's another state?
Different states for different roles of the users.
Okay. Okay, so for different classes of users, or
Yeah, there'll be different classes of users.
that's right. So there might be a user who's a cleaner and sees one thing. A user is a doctor and sees a different state. Okay. Maybe cases where a person just browsing versus editing some elements of it. I'm not trying to force fit this, but you should be able to think abstractly about, okay, what different situations does the software have to respond to? Like, what modes is it in? What sort of types of interaction might be handled? And it may be that there's a doctor mode and there's a transition, which is you modify something, or maybe there's actually a state like you're in the middle of modifying the bed status. You're entering when it will be available, or was it cleaned? Maybe there's a state where you're actually specifying some information. But whatever your system is, it's quite common that you can formulate a diagram like this. Here's another one. Okay. Here's for making flight reservations. Okay. This is a somewhat older one. Where we had more printed tickets. Still, people print boarding passes in many cases in case their smartphones run out of juice or what have you. Okay, so here, you may make a reservation and then you actually pay for it. The reservation is held for a certain amount of time, and then there may be some formal ticketing which goes on. Again, in some international routes, this is still done, and there may be several reasons that a given transaction may be canceled. Just because they're both canceled doesn't mean they're one state. There may be cancellation due to non-paying, as well as cancellation by customer by request. And then there's cases where a ticket is used versus attempted refund. And here you have a set of different states. You have the made, paid, ticketed, used, canceled by customer, canceled for non-paying reasons. And then you have transitions between them. These transitions are actions. Someone has canceled it actively, or maybe it's just timed out. It's a passive thing. Maybe they've sought a refund for a ticket, or they've obtained the ticket and they use it. Now, we're going to talk about several types of coverage for this in things like the preceding diagram. What is state coverage? Here, we're sort of covering an embarrassingly small number of things. All we're doing is we're making sure we hit each of these ovals, ladies and gentlemen, at least once. Okay? We're making sure we hit each of these circles at least once, right? That's state coverage. And if you folks achieve state coverage in your testing, I'll be happy with a certain level of confidence in the system. If you haven't achieved state coverage, I'll be skeptical. I'll be skeptical that your system's working. And again, if you never tested it in a state where it's canceled by customer, how do you know it's going to work when someone seeks a refund or what have you. But we're going to talk going beyond that, per Evan's comments, about transition coverage, which is something a level up from that. Here, we're not just trying each state that we're in, we're actually trying all the transitions between the states. So yes, this cancel by customer can be obtained in 3 different ways, right? It can be obtained by canceling this reservation before they pay for it. It can be paid but before it's ticketed, and then canceled when it's already ticketed and they want to just back out. You know, Orbitz, for example, has within 24 hours of purchasing a ticket, you back out for free. In fact, you can back out for free. You might want to test all 3 of these methods because they are rather different. Here, we don't even have to refund a person's payment. Here, we have to refund the payment, but we don't have to unticket it. Here, we have to unticket it and refund the payment. So there's rather different actions associated with these. And by testing these transitions, you can get a greater degree of confidence about the system. Similarly, let's go back to this guy here. This guy here. This confiscate card, it can be reached by several different ways, right? It's lost. It's expired. We've tried the PIN too many times. State coverage would just get us to one of those and say that's good enough. But we might want to test each of these because they're things of considerable gravity, right? You want to make sure that if the card is lost, it's still confiscated, right? To make sure that people aren't traipsing around with other people's cards or what have you. So I will be a much happier camper yet if you achieve some sort of transition coverage within your system. At least I'll have some confidence you're testing the different conditions under which you can enter a given state. For example, there may be a state associated with drawing on an existing canvas, and I want to be confident you've tried it with the connector, and you've tried it with the intervention symbol, tried it with the variable, tried it with the parameter, tried it with each of those, dragging those in there, that you might get to the state where it's sort of updated. So transition coverage is important, okay? Another case. Now, ladies and gentlemen, in the closing minutes of this session, I'm going to prepare you, maybe even steel you, to what we're going to be covering next time in terms of coverage. And there's a general rubric here. It's a general pattern, okay? Regardless of whether we're capturing states, or getting to cover states, or we're covering transitions, or regardless of whether we're covering paths, as I think Evan presciently anticipated, perhaps, there's going to be a couple key steps, and I expect you to know these steps because they're common to all of this. So first, we identify a set of things we need to cover. Maybe it's states, maybe it's transitions, maybe it's paths. Then we're going to develop a set of abstract scenarios, often paths, that will include all these things we need to cover. We're going to have to think, okay, we can go this way, we can go that way, we can go this way to cover the states or to cover the transitions. And then, ladies and gentlemen, and this is often where it gets really textured in a particular case, you develop a set of test cases, very concrete cases, like what input do we have to give to this system? What do we have to do to it to actually cover these paths? So these are abstract paths. We go through this, we go through that. We're going to have to here unpack that into like, what do I do? What do I press? How long do I wait? Or what have you to get to these places? What do I drag in? What buttons do I hit? What do I type? What have you? Okay? So figure out what to cover, a set of paths through the system that will cover them, a set of concrete cases that will exercise those paths. Now, a key issue is those test cases may exercise other paths too, on top of the ones we want, and that's fine. But at least they get us through the system in the desired way. And these are going to be the actual tests you'd run to exercise the system. Okay, so let's go back and talk about this here. Okay, how about this one here? It stands before us. So, ladies and gentlemen, suppose I wanted to reach all states. Or no, excuse me. Let's suppose I wanted to reach, I want to test this transition greater than or equal to 3 tries. It's one right up there towards the top. So tell me a concrete thing I can do to reach that transition. So these are all the transitions I want to reach, these ones with arrows. What do I need to do in order to reach this one? I actually want to have a use case scenario where I can reach this one. I may say I want to reach this, but in order to get there, in order to get to that point, I need to start somewhere. I need to start at the start, right? I mean, I can't just come in and say greater than 3 tries and see if it confiscates the card. I have to do something to the system. So I'm going to have to figure out. So I see all these arrows. Those are the things I want to cover. Now I'm going to figure out paths through the system that will cover each of those arrows. I'm going to have to figure out a path through the system, for example, which will cover this arrow as one of them. And I might do something like, I might define this path here and go back and forth until it's 3 tries and then come here. That would be an obvious sort of path to try. That path from the start to a finish will exercise this particular case. Okay, so that's an abstract path. From here, I go down here, it's been 1 try, 2 tries, whoa, oh man, 3 tries, boom, I go to here. Okay, that's an abstract path. That's the path I want to take. Now, how am I going to do it? Tell me what to do. What do I do?
You need a recognized, not expired, not lost card.
Good.
As input.
Excellent. I love it. Your name?
Evan?
Okay, sorry. I couldn't tell whose voice was emanating. Okay, yes. Okay. So we want to start with a card that's not expired. It's not lost, right? And what do we do then? And it's recognized.
Put the pin in wrong 3 times.
Put the pin in wrong 3 times. So we need to know, well, we either need to know what the pin is and not enter it, or we need to, re-enter the same broken thing 3 times that happens to work. We guess what's not the pin, which is a pretty easy thing to guess, right? Okay, so we do that 3 times and that will get us there, right? We enter it and it will loop around. Those particular actions, and you might enter a particular pin, you might say enter this, 1 1 1 1 1 1 1, and then do it again, 1 1 1 1 1 1 1 1 1 1 1 1 1 1. Sucked up, okay, in the confiscate card. Okay, suppose we wanted to, for example, get to this transition here, daily amounts exceeded. We're going to need to figure out some way to get through this system that will get down to daily amount exceeded. Give me a test case that might do that. A particular concrete test case. I'd argue there's many test cases that would get us there. Give me one. So we want to be sure to test daily amount exceeded. All these transitions we're going to cover, so there should be at least one path to test this. What would it be? Give me a plausible case.
Well, you could start by withdrawing a bunch of funds, and then once you've exceeded the daily thing by trying out the other things by withdrawing a bunch of cash, then you've got it to the point that the daily amount is exceeded, and you know it works because you're just withdrawing cash.
Okay, so I like that. There's no loop back in this particular one to the
Yeah,
beginning.
it would require using the card multiple times.
Require using it multiple times. Okay, let's start on the last time you do that. Let's suppose that you have set it up so that, and by the way, that's an aspect of sort of getting the test harness ready, the test situation ready. So we start here. We want to test this out. What's an abstract path that will get us there? Give me one. Well, go along here. I'll do it on the screen here so it can be recorded. You come along here, right? You go down and come down here, and make sure you're coming down and entering this. Okay, so that's good. Is that the only abstract path that would test that? What? Give me another abstract path that could test it.
If you enter the pin wrong once
You
and get it right the
Good.
second time.
You enter the pin wrong once and then loop down. So there's several abstract paths that could cover this. Pick one of them, and now we have to figure out, in concrete terms, how are we going to realize that? How are we going to make that happen? And that might involve, particular pin entry here, entering the correct one, or after one time entering the correct one, coming down here, selecting withdrawal, right, rather than other things which lead to other paths. And it has to be for a valid account. You're selecting an account number, and at that case, if you have set it up so that there's insufficient funds, you'll get this. So it requires going from abstract paths to concrete things you are entering at each step, like selecting, withdraw, etc. Concrete test cases. And ladies and gentlemen, we're going to use this basic rubric for you to try to come up with test cases that are going to test the states, or better yet, the transitions of your system, including paths between web pages on a web app or between screens of your app on a device. So that's the goal of this next lecture that I'll be giving on Thursday, to give you some sense about how to accomplish these things. Okay? So we'll be meeting on Thursday to do that, but I'll be seeing you later this afternoon for the presentations. Right? Very good. So I'll see you here at 4 o'clock.